Hi, my name is Jim, and I'd like to talk about the Stern-Gerlach experiment. I'd like to talk about the Stern-Gerlach experiment for PhysicsFM. PhysicsFM is a podcast featuring my friend Randy and me talking about selected physics topics. Right now what we're doing is we're reading a book called Quantum Paradoxes by Aharonov and Rohrlich. It's a very interesting book. What it does is it uses the artifice of a physical paradox both to explain quantum mechanics and to argue for a specific interpretation of quantum mechanics. It's a very effective device. So what we do at every podcast is we talk about one chapter in quantum paradoxes, and we talk about the main paradox in that chapter, as well as what that means for quantum mechanics. And this paradox is based on some experiment. So it's a physical paradox, has to be based on a physical experiment, something that somebody could possibly do, or at least somebody can imagine themselves trying to figure out some way of doing. So there might not be a real way to do it. It may just be a Gedanken experiment, but it's still basically a physical experiment, and it has a physical geometry that we're trying to convey in an all-audio form. And that doesn't really work out very well. So this podcast, or this video, is intended to help you understand the physical geometry of the Stern-Gerlach experiment, to understand, and also to understand some of the physics behind it, just in a more systematic way than would happen in a natural conversation like Randy and I are having. So let's get on with it and talk about the Stern-Gerlach experiment. That sounds like a great idea to me. So the Stern-Gerlach experiment I'm choosing, it's used several times in the book. It's used in 3 chapters of the book, I believe. And it's also one of the experiments, the Stern-Gerlach device at least, is used in one of the recent podcasts I uploaded, so I chose to do the Stern-Gerlach experiment. It's a very useful experiment. What it does is it shows, the original Stern-Gerlach experiment showed that the angular momentum is a quantized variable, right? That it can only occur in certain steps, right? There are certain chunks of angular momentum in some way. What exact way that is, I'm not going to tell you right now. Maybe I'll save it for later. But that's what the point of that experiment was. And it turns out to be a very useful experiment pedagogically as well, right? It's very easy to explain things like how the how conjugate variables work, for example, or how uncertainty relationships work using the spin, using the Stern-Gerlach experiment, and how it interacts with different effects. So I'd like to do a later video possibly on that, but right now I'm just going to talk about that experiment, all right? And it's going to be very useful if you're either listening to the podcast or possibly if you're taking a quantum mechanics class, because I don't think the experiment gets as much detail as you probably would like, because you know, if you're in a class, you've only got so much time and a whole lot of material. It's amazing how much material you go through in a college classroom, right? So I'd like to go through this experiment, just go through the physics behind it. You know, what it acts on. It acts on objects with magnetic moments, and how that works physically. That has some sort of magnetic force associated with those magnetic moments, by their interaction with the magnetic field. And then I'll go through the experiment after I've told you, you know, the things that it acts on and how it acts on. Right. So that's what I'm going to do. It's all right here in the table of contents above my head, so you can use that to, you know, keep a tab on where you actually are, where I am while I'm talking to you right now. All right. So you know, the magnetic moment of an object is something that shows up, at least classically, whenever you have an object that both has charge and mass in the same place, right? So if it has a charge distribution and a mass distribution, whatever that is, you could think of that as maybe a sphere with, you know, a uniform density and a uniform charge, or you could think about it like what I've just got here, which is a plate of uniform mass with a wire of charge, a charged wire, sort of glued onto its edge. And that's going to be able to give us a magnetic moment if this plate has some angular momentum. And right now it doesn't have any angular momentum because I'm not rotating it, but once I do start rotating it, right, now that charge actually becomes a current, right? And that, if you've taken a physics class before, tells you all of a sudden that, yes, that's going to create a magnetic field, and it's also going to react to a magnetic field. And the strength of that reaction is basically the magnetic moment. And that's sort of how we define what a magnetic moment is in physics in general, is through these current loops. So if you look at a book on magnetism, you'll see a lot of talk about current loops and things like that before they get into the real meat of the book. So now the faster you rotate the charge, right, the larger your current, so that means the stronger your magnetic moment. And so that's where this idea that the angular momentum, which is based on how fast it's rotating, and the magnetic moment are proportional. And they're proportional in a very specific way. I have written an equation down there for you. The only important thing about that equation is that there's a little factor g there. That's just a number. Everything else is completely defined. And you know, if you have a solid uniform volume charge with a uniform density, that equation with g equals 1 is exact, right? And everything makes perfect sense. It doesn't matter what the shape is. It doesn't matter what axis it's rotating around. Everything is just the way that's written down there. And then that g factor has to do with the differences between the distributions of the two different kinds of densities, right? The mass density and the charge density. So if you look at this particular setup, which is probably the easiest setup to do the work on, you can figure out that for this rotating disk, that g factor is 2. It has sort of twice the amount of the magnetic moment that if you smeared that charge over the plate, it would have. All right, that's all that g factor means, right? Another one that I'd like to look at here is a solid sphere with a uniform surface charge. So now I have a solid sphere and I've smeared the charge all over its surface, and then I spin it around. It doesn't matter what axis because it's a sphere, right? In that case, g is 5/6. Now, the reason why I have that last one, as well as, well, for some other reasons, but for these two particular ones, I left that there because they have to do with how the electron works, right? So if you were to make a classical model of an electron, you'd say, well, you know, we know from experiments that it doesn't look like the electron has an electric dipole moment, so it must be a very spherical object as far as its charge is concerned. Everything that we've looked at sort of says that the electron is an extremely spherical object, right? It's also very small. We have a limit on how big it can be. We don't have a limit on how small it can be. So it could be as small as 0, right? It could be infinitesimally small. And it could be up to this really small number, which is something on the order of 10 to the minus 22 meters. It's very, very small. It's probably even smaller than that now, but it's some number on that order is the largest limit that the electron radius can be. But if it's a classical object, if it acts like a billiard ball, right, then it should have a g somewhere around 1 or 5/6 or something like that. Instead, it's the electron's magnetic moment has been measured so that that g factor is 2.0022 blah blah blah. It's got plenty of numbers back there. It's a very, very well measured number, partially because it verifies the theory called quantum electrodynamics, which is a relativistic theory of quantum mechanics, which is not what I'm talking about here. And so that's an extremely accurate quantum mechanical number and it's a measured number, and it says basically that this electron is quantum mechanical in nature. It's not classical. It's not a little hard sphere at all. Whatever it is. We don't know what it is, but whatever it is, it's a little hard sphere. It's not a little hard sphere, right? And it has this magnetic moment, but it's not from the electron spinning, right? We don't know where that angular momentum is. We call it the spin angular momentum. That's why I left the S in that equation. But we don't know why magnetic moment occurs. Okay, at least it doesn't work in that same way. It's a fundamental property of the electron, the same way the charge is. You're stuck with it, right? Now, I usually run into this electron stuff when I'm working with ferromagnetic resonance, which is an electron spin resonance technique. There are other resonance techniques, spin resonance techniques, like MRI, right? Nuclear magnetic resonance imaging that uses resonance of the nucleus. And so you might want to know what the G factors of the proton and neutron are. I've left them there for you. But remember that the neutron, even though it's neutral in aggregate, right? It has component particles, so it should have some distribution of charge inside it. It's just not charged in total, all right? It doesn't have a total charge. Anyways, that's my explanation of the magnetic moment for you. That's why the magnetic moment comes about. And now I want to talk about how that magnetic moment reacts to a field. So I'd like to start off just by talking about how it reacts to a magnetic field, right? A magnetic moment only reacts to a gradient magnetic field. And what that means is it only reacts to a magnetic field that's changing. You see the magnetic field that I put here? This magnetic field occurs when that little silver bar at the bottom is a wire that has a current coming out at you, all right? So that current coming out at you creates this magnetic field. So if I had a magnetic charge, and there's no such thing as a magnetic charge, but we're going to pretend like there are magnetic charges just for a second so we could see what would happen to them in a magnetic field. And what would happen to them is the positive charge would follow the electric field in the same, or the magnetic field in the same direction, and the negative charge would follow it in the opposite direction, just the same way that an electric charge would. But again, there are no magnetic charges. This is just what they would do if they were in that field. But if you were to model you can model the magnetic moment then the same way that you can model the electric dipole moment, right? And so the magnetic, you'd say, okay, there's a magnetic charge at either end. And if that were the case, then what would happen is that if I put this guy here in this field, he wouldn't move at all. And why is that? That's because the positive charge would want to go to the positive charge would want to go to the left, the negative charge would want to go to the right, and you wouldn't have any net force on the object. And now what would happen is that the object would rotate, right? So you see, it would rotate just like this, so that the object would try to align with the magnetic field, right? And that's what happens in a uniform field. The magnetization of an object, the magnetic moment of an object will try to align with the magnetic field. It won't be pushed along it. That's how a compass needle works, right? Compass needle will always try to align with that magnetic field, and it doesn't matter which way it originally started at. It's going to want to rotate along the direction of the magnetic field. So that's all that's going to happen to these guys in a magnetic field. Now, when I'm going to do this experiment later on, I'm not going to let the magnetic moments change their direction. I'm just going to force them to stay in either in some direction, whatever that direction is. Now let me look at these two guys, right? So now I've changed this so that I have a magnetic pole piece here that comes to a point. If you have a magnetic pole piece that comes to a point, it's going to act like a linear distribution of magnetic charge. Now, there is no linear distribution of magnetic charge. That's just how it's going to act like. All right, so you're going to get a radiating charge, a radiating magnetic field like this. This is about as close as you can get to a line charge, a charged wire or something like that you can get with an electric field. This is actually part of the experiment. So you're going to have two magnetic pole pieces. You're going to have one pointed like this, and then you're going to have a flat one up here. It's going to create a gradient field. What that means is the field is changing. And what's going to happen in this particular case is if you're up right down here, the positive or the spin up, the one that's going this way, is going to move that way. The spin down is going to move down that way, right? They're going to move in opposite directions. Feel the same force, and they'll move in opposite directions. But because this magnetic field is changing direction, the gradient is actually changing too, right? And so the magnetic force will go something like that. It'll force the magnetic moment to start, if it starts here, off to the right of this pole piece. It'll move along. It'll be going horizontally exactly at this 45-degree angle, and then down here it'll start going straight down. All right, so that's that's sort of how the force is going to pull that magnetic moment around. But the important thing that you're going to want to remember is that in a field like this, where you've got the line radiating out here, that's about where we're going to send our beam of silver atoms in the Stern-Gerlach experiment, is along this vertical line. What's going to happen is a silver atom that has an upspin is going to go down, and the silver atom with the downspin is going to go up. All right. In this case, if the magnetic field was going into that point, which it could do, all I have to do is reverse the magnetization here, reverse that black arrow, then it's going to go the other way. So that's exactly how this experiment is going to work. We're going to send a beam of silver atoms. We're going to send a line of silver atoms into a magnetic field, and we'll split the magnetic. It'll split up the beam based on the magnetic moments. All right. So now we know about magnetic moments, and we know about the magnetic force on those magnetic moments and what's going to cause it. It's going to be this gradient of the magnetic. It's going to be the gradient of the magnetic field, or more precisely, that the projection of the magnetic moment on the gradient of the magnetic field is the magnetic force. All right. So I think that's clear enough for now. Let's try to finish this up. All right. Let's talk about the experiment. So in the experiment, what's happening is we've got this oven, and we're heating up a bunch of silver atoms. All right. And these silver atoms, they gain a whole lot of, well, they actually evaporate. So you're boiling these things off in a sense. I'm not sure if they're actually melting, but they are boiling off silver atoms. They're ejecting silver atoms from this oven, atom by atom, right? And they run off with a random velocity, a random momentum in all sorts of different directions, right? And they also have a random magnetic moment, all right? So everything's randomized about them. There's no reason why they'd have magnetic moment in one direction or another. There's no reason why they'd have a velocity in one direction or another. And we're going to want to use that magnetic moment bit, and we're going to want to constrain that momentum bit. All right. So first, let's just talk about what the Stern-Gerlach experiment wanted to test, and it wanted to figure out if the magnetic moment of these atoms was quantized or not, because it was testing the Bohr-Sommerfeld theory. Right. So that's basically what we were trying to get at. So what would happen is, if I would later on put an applied field on these guys, the possible magnetic moments available in a classical sense would be any one, right? The projection of the magnetic moment on that applied field, it could be any number, right? Could be anywhere from its maximum moment to its minimum moment, and it could have any angle in between. Any of these angles would be okay for one of these magnetic moments. So that's why I have these two arrows here. And this bar, this sort of peach bar, that is all of the values from maximum to minimum. The magnetic moment could have any of those values in the z direction, in the applied field direction. Quantum mechanically, that's not true. In fact, you can only have two values, and they're not quite at that maximum. And that's the reason for that is something to get into at some later date. But you only get two possible values, and those we call spin up and spin down generally. Spin up is when that projection is in the same direction as the applied field. Spin down is when it's in the opposite direction of the applied field. All right, and so you only get these two values. Now, one of the questions that people have had when I've been talking about this is whether or not this can ever directly point along the applied field, because they've listened to people talk about magnetic resonance in the past, and when you're talking about magnetic resonance, when you're talking about MRI in particular, you're talking about pinging the magnetization of something and letting it ring down and return back to pointing along the applied field direction. That's not actually what's going. That's not what's going to happen to any particular object, any particular magnetic moment. All right. If you only had one magnetic moment, it would never quite get to aligning along a particular direction. But if you have many, many of these moments, if you have 10 to the 20 of these moments, then they're transverse directions, right? The directions perpendicular to the applied field are still randomized. And since they're still randomized, those transverse directions average out to 0. And so maybe I'll talk a little bit about magnetic resonance in a later video or something like that. But what happens is you have these two different decay times, T1 and T2, and one of those decay times is specifically how long it takes these things to realign with each other. The other one is how long it takes them to dephase and to lose the phase information that occurred because of because you hit this thing with a very short magnetic pulse. So that's actually built into the MRI, is that these particular values for each particular moment has to have one of these values, and then it will relax down to a particular applied. It will relax down to pointing the applied field on average, even though none of the constituent particles are pointing directly along the applied field. All right. So what are we going to do with these things? Like I said, we want to get a bunch of these silver atoms in a line. So we've randomized the silver atoms, and because of the way we build up the atomic shells, right, with the exclusion principle, we end up with two opposing magnetic moments for each particular quantum number, right? So that means that each one of those two cancel out the magnetic moments. And then it's only that last unpaired electron in the silver atom, that 27th of 27 electrons, that has a magnetic moment that is going to interact with this magnetic field. So we're going to get these moving, and we want to get them in a nice tight beam. So if we can get them in a nice tight beam, then we can do something to the beam and figure out if anything's happened to the beam, right? If we just have a bunch of things randomly going off in all sorts of directions, then it's going to be very difficult to tell what happens to these atoms unless we have a reasonable way to collect that data. It's much easier to just put a slit in here in this collimator and put this collimator in there and end up with a line of atoms that are all going in one direction and block off all of the atoms that are going in the wrong direction. And you can see with this picture on the right what actually happened in the Stern-Gerlach experiment with no field on, right? You just got this line. And I've schematically represented that by a little white line to the left of the picture. We just get this white line with no field on, and that's going to deposit on the plate. Every time an atom comes and hits the plate, it'll stick, or at least there's a chance that it'll stick on the glass plate. And more of those atoms keep hitting on that plate, and eventually you get something that's actually visible. You get a visible line of metal on that glass plate. And this is actually how people develop films for use in, say, the magnetic recording industry today, is they throw one atom at a time, usually of a magnetic material like iron or cobalt or something like that, and just keep hitting a substrate until it builds up a thick enough layer that the people who are doing all this engineering can actually use it. And it's also used in research and things like that. So this is just one way you can deposit a film onto something. And it was already being used for experiments 100 years ago, right? So now what we want to know is what happens if we put an electromagnet in there. So I've got this electromagnet in here, and we know what would happen if I had no field on, right? So what would happen if I did put a field on? Well, I need to put on a field that has a gradient field, and so I'll use a pole piece that looks like this in cross section. And you'll notice that very, very close to that point of that triangle, everything looks like it did in that picture I was talking about previously. And we could talk about details of all of the field lines here. They're not really that important. What's important is that, you know, along this central line there is a field gradient, and that field gradient is nice and reproducible and something that we can use. So, like we said before, if there is a field gradient, that means that you know, atoms with that last electron having a magnetic moment pointing directly with the beam will go up way high. One directly opposite with the gradient, excuse me, will go down way low. And so the only question is will there be something in the middle, right? So if we had a classical vision like we saw earlier, where we could have had any particular projection of the magnetic moment of the silver atom on the applied field gradient, then we'd end up with a big filled-in circle, right? We'd have a big filled-in circle deposited on that plate because, you know, we'd have forces of all sorts of different values. However, if we had a quantum mechanical treatment, there'd only be two possible values, and so this thing would open up. There'd be a big area in the center here. Possibly there'd just be two lines and nothing in the middle. It depends on the initial momentum and of the silver atoms and the size of that slit, right? So there are a bunch of different factors on exactly what it's going to look like, but basically you'd either have a big solid deposit, or you'd have a ring or a split deposit of some kind. Classically, quantum mechanically, those are your choices, right? And so what happened? I mean, you're dying to know by now because you've been listening to me jabber on for 25 minutes. Bam! So this is what this is what they got, right? And this is a postcard that they sent off to show off their data, and I've put the results right next to our predictions, and you can see that there's a big hole, a big white hole in that deposit where nothing actually hit the glass. Nothing went onto the glass. So what we ended up with is the quantum mechanical prediction, which is good because otherwise we probably wouldn't have this video. So you have this quantum mechanical effect going on and showing up in this Stern-Gerlach experiment. And that's the reason why, and that's how it all works. And now you can take a bunch of these in series and do things with them and make paradoxes, right? That's something you can listen to in the podcast, and it'll make a little more sense, I hope, now. Again, you know, why do I think this is a very useful experiment? Well, first of all, it's very useful pedagogically. It's very easy to use this to teach about conjugate variables and uncertainty relationships because you only have two values, right? You've only got spin up or spin down. You don't have to worry about things like position and momentum, which have continuous variables. So first, you're just starting off with very simple effects that can be represented very easily by a matrix, rather than continuous values where you're going to need to throw a differential equation at somebody on day one of the class. Just say, this is the Schrodinger equation. We're going to stay with this for the next 4 months. I hope you love it because I do. And you should love it. It's a wonderful equation. It's just that it's not the best introduction to a lot of the things that you're going to see. And this has a much more natural, I think, interpretation for most students. It's also used in quantum paradoxes, for example, for a model of quantum measurement. It's a very interesting model of quantum measurement, or very interesting way to do that is just go through this one experiment and show you what's actually happening and how that relates to, say, the von Neumann model of quantum measurements. It's very useful. That's what they do in quantum paradoxes, and something I might explore here later on as well. It's also a viable model of the EPR paradox. That is, the Einstein-Podolsky-Rosen paradox, which is so important to how we interpret quantum mechanics, was originally devised by Einstein, Podolsky, and Rosen in a way that did not look like it would be something that you could ever set up. It had a nice Gedanken experiment that didn't look like it would ever turn into a real experiment. Well, when Bohm wrote his quantum mechanics book in, I think, the 1930s, he inserted a description of the EPR paradox using the Stern-Gerlach device. Used a few Stern-Gerlach devices to show what happens with these entangled particles and so forth. So that's a very important thing. It's a very interesting way to do it. And I'm sure a lot of you have a copy of Bohm's book available either at your college library or even at Barnes and Noble. I mean, Bohm's quantum mechanics book is available from Dover Publications, so it's cheap and readily available all over the world. So you might want to look at that. I'm also reading a book right now about decoherence, quantum decoherence, and that uses the Stern-Gerlach experiment all over the place as well. Just talking about how decoherence works, which is another way to talk about what happens with quantum measurements. So if you're interested in any of these things, I think that it's probably a good idea to have a good background on the Stern-Gerlach device. And I hope this has been helpful for you in trying to figure out what the Stern-Gerlach device is and how it actually works. And it will help you, especially if you're listening to our podcast, like right here at www.physicsfm.com. It's a great place to listen to our podcasts. And I think this might help you a little bit. And if you want to learn more about how that works as far as the quantum measurements are concerned, just, click on, there should be a link below down here somewhere that will take you to our podcast number 7, which talks about chapter 7 of quantum paradoxes, right there. And so that particular chapter is all about how quantum measurements are made, and Aharonov and Rohrlich again use the Stern-Gerlach device for that. So you're ready for that right now. So go ahead and click. You don't have any excuse. I hope you enjoyed this, and comment if you see anything a little bit off. There have been a lot of things off so far in making this. This is maybe the 4th one I've uploaded and the 8th full take. And, you can go to the Reddit, make suggestions about other things you'd like me to talk about, whatever you want. I mean, just, give me some feedback, and maybe I can make future presentations a little bit nicer for you, and maybe I can talk about things that you think would be a little more interesting, or you would find interesting if you just suggest them to me. So anyways, I'll talk to you later. Thanks for listening. Bye now.